audio setting. It's all good. The mic. All right, so I'm going to get started with cisp310. And today we're going to review the final exam. And also, if I have time, I want to give you guys the solution to the homework assignment. I may not give you the entire homework solution or the solution to all of the questions. I may just implement ABC because that's probably the most difficult one to deal with because it's a combination of all of the other ones. So, so let's take a look at what time we have or how much time we will take to go over the practice exam, which is the actual final exam of spring 2015. And once again, it is just a hyperlink into apps.losreals.edu. So if you want to look at the document at the same time, you have to sign in first to apps.losreals.edu. But you can just look at the screen as well if that's what you want to do. All right. So we'll zoom in. Zoom control. I missed the zoom control. Oh, right here. Staring me in the face and I missed it. All right. So just the basic stuff, this part really has not changed much. Even the time is going to be the same. It's going to be 8 to 10 o'clock on next Tuesday, 1 week from today. So you might want to make sure that you get enough rest before the exam and just be well prepared. It is open book, open notes, okay? So you definitely can bring in the material, including everything that we have talked about, okay? My solution to all the homework assignments, if you want to bring those in and think that might be helpful, bring those in. Yep, question?
Like this is a bit off topic. Has exam 2 been graded yet or not?
It's in progress. Thank you. But
I was worried about that when I didn't see a grade. I just thought it was me.
Now, I do want to make sure you guys know where to find the solution or the answers to the second exam because that part is important.
It's that Thursday lab section, right?
Right. So the lab session is the actual solution. So you definitely want to know the correct answers to all of those questions. If you use additional sheets of paper, once again, I talked about this in the previous class. Make sure you write your name on it too. So this way, if I manage to lose track of the loose paper, I still know, how they are supposed to be stapled. Write legibly. Okay, that's kind of important. I have to tell you, when I scan all of these and have to type in the name to name the files. I would say at least 10 students out of each class, I cannot really fully read the name, so I have to look up my roster and say, I think that's the closest match. Let's just say it's that person. Write legibly, all questions have equal weight. The exam counts for 40% of your final grade, and once again, you need 37.5% to pass the class with a C. Clearly indicate the base of numbers. So in case you want to indicate the value of something and you want to use base 16, make sure you start with 0x. If you want to use auto for whatever random reason, start with a 0. And if you want to use binary, do a 0t as the prefix of a binary number. And this is how I consider what is correct code. So you might want to keep track of this one, and because you can study this before the exam, I strongly recommend that you understand what I consider correct. The stack remains balanced, with items cleaned up immediately after use. In other words, if you call a subroutine and the parameters are no longer useful, clean it up, okay? The correct flags used for signed versus unsigned numbers, even if the range of numbers being tested may not trigger incorrect behavior. So pay attention to whether it is signed or unsigned. The assembly code is logically the same as the C code if the C code is provided. So do not implement your own way of doing things. It has to match the C code. Registers assumed saved by callee remain unchanged when the callee returns. So if you are writing the code of the callee and you decide, okay, I need to use EBX for something, make sure you save and restore EBX. Because from the caller's perspective, EBX is supposed to be preserved. To reverse engineer code, the C code should not contain any go-to, continue, or break statements. So make sure your C code itself is fully structured. All subroutines should make use of the frame pointer. So even though you might find a way to implement something quickly, quick and dirty without using frame pointers, your answers should still use the frame pointer. All callees written in assembly should work with either caller code written in C or assembly language. So you have to follow all the rules of being callable from C. All caller written in assembly should work with caller. We just went through that. Isn't that exactly the same? Oh no, all caller and versus callee. So it has to be interchangeable. No corruption of memory locations, assuming incoming parameters are correct. So that means your code it should not contain code that can corrupt memory. So corrupting memory means EBP is corrupted, or the return address is corrupted. So do not corrupt any memory that is not the subroutines. None of the compiler, assembler, nor linker should produce errors, and I should say or warnings. Okay, so make sure that your code is considered correct from the perspective of these tools. All right, so here's question 1. Question number 1 is to find and fix all the problems of the assembly code implementation of the following subroutine. And the actual code is missing, isn't it?
Yeah.
Yes. That seems like one of the first problems.
Yep, that would be a problem. Okay, so in this case, it has pointers and a pointer to a function. I'm not going to ask anything about pointer to functions because we haven't really talked about it in this class. So it may not be relevant anyway, because we haven't talked about this particular construct in C. How many people know this already? It's just that you haven't seen it in assembly code. So 1.5 people. Okay, 2.5. Okay, so we have 2.5 people with some exposure to pointers of functions in C. For the most part, it's not needed anymore, and maybe that's why you guys have not been exposed to this concept, because C++ is supposed to provide a much better way of doing things rather than passing the pointer of functions. So that's why many of you do not have any exposure of this concept, because this was necessary before C++. Yeah, go ahead.
So this is like a BST, right? Like kind of
a BS.
Like kind of like a binary search tree setup, or.
Possibly. I don't even know. It has siblings. It has child, so it's definitely a tree kind of thing. But this probably came from a program that was done in that semester. Question number 2, reverse engineer the following assembly code back to C. Assume all labels are properly defined. The C version must have the proper return type, parameters, local variables, and so on. Okay, we have seen this already in exam 2. Okay, so let's go ahead and figure out this one. This one is kind of useful to figure out because it has some concepts. Many of the concepts that we have talked about in this semester is already here. There is one concept that we have not talked about that is here. Okay, so let's go ahead and work out this one. And I need to figure out the best way to combine my tools. So I'm gonna try out this way here. Right to you.
You used a different option last time you did this. Instead of the transform.
Yeah, okay. This one doesn't look right. So get rid of this, use transform. Yep, much better. It preserves the aspect ratio correctly. Okay. Okay. So to try an empty page. Okay. And then we move this one next to the original C code. Now we can work on it. All right. All right, so let's work on this one. And what we would need to do is to say, okay, this one is a little bit non-traditional. It doesn't even start with the instruction that we are familiar with, which is a push EBP. Well, what do you think? When you look at these two instructions here,
Yeah.
as a combination together, what do they do?
Push EBP.
Push EBP, exactly. We subtract 4 from the stack pointer first, and then we copy EBP to where the stack pointer is pointing to. That's exactly a push EBP. So this is really testing to see if you guys understand that sometimes using a RISC method, we can do the same thing but without using the instructions that we are quote-unquote familiar with. Okay. All right, so push EBP is here. And in this case, we're not spotting problems, so this cannot be a problem. It has to work. It's just that you have to figure out, oh, we haven't seen this before. Wait, we know what this is. Okay, cool. Okay. And then this part here is adding result to ESP, which means we have some kind of a local variable. So if I were to work on the C code, I would start with node sum and open paren, close paren. It has some kind of return type. I leave the space for that. And I know that we have at least one local variable result because we use that to adjust the stack pointer after move L ESP to EBP. Is that part okay? Now, what is the type of result? I have no idea. Okay, based on this, I don't know yet. Okay, so the first thing we do over here in assembly code is without inside any loop. How do I know this code is not inside a loop? There's no label before that. Okay, if there's no label before it, it cannot possibly be in a loop. So we are just initializing result to 0. Okay, fine. We'll just say result equals to 0. Okay. Now that really doesn't tell me much about the type of result because it can be a pointer, because that can be a null pointer. It can be an integer, can be assigned, or can be unsigned. So I cannot really come to any conclusion yet how to interpret that. And then the very next thing we do is to compare parent as something to 0. Okay, so we have parent inside some kind of comparison with 0. But hold on a second here. Where's parent coming from? Can be a parameter, can be a local variable. I cannot differentiate at this point, but I know parent is going to be one of those two. Can parent be a global variable?
Yes.
From the way we use parent as a label, can it be a global variable? Nope, because it is relative to EBP, which means it is in the current frame, which means it can only be a local variable or a parameter. Okay. So we're comparing parent to 0. If it is 0, we go to end if, or if end, and if end is all the way down here. Okay, so that means, sounds like a conditional branch to me. Sounds like a conditional statement. So I can say if parent do something, and this is the end of the conditional statement. And at the very end of the conditional statement, you can work on that part too. We are just copying result into EAX. What do you think is the purpose of copying the result into EAX? It's the return value. Very good. Okay. So that means at the very end here, should I use else? Looking at the assembly code, the move L result EBP EAX is after if end. So should I use else over here? Nope. No else. Okay, this is just return result. Okay, and that's the end of the entire subroutine. So now I have to figure out what is in between these two curly braces. So going back to the assembly code, now we work on the code inside the parentheses or inside the curly braces. Inside the curly braces, the first thing we do is something like this. What is that doing? We've seen some code like this already. What is it doing? It's pushing parent, okay? And just seeing this, okay, what is this reminding you of? What are we gonna do?
Local variable.
We're gonna call something, okay? We're pushing parameters. So we're calling a subroutine, and the subroutine turns out to be node sum itself. It doesn't really matter whether it's recursive or not. It's just calling a subroutine. So this is the last parameter. Remember, the last parameter is pushed first, and then the first parameter is this thing here. Okay, we are pushing it. Just having a little problem. Oh, wait, there's only one parameter that we're pushing. We are subtracting 4 from the stack pointer, which means we're reserving 4 bytes on the stack. But the next instruction doesn't move anything into the stack at all. It is just initializing EAX. So it's putting parent into EAX, and then it uses EAX as a base register, and then use this notation here to say, hey, let's go to that place, and then use that and put that into EAX. And then we actually push EAX on the stack because we're copying EAX to where the stack pointer is pointing to. So the question is, what exactly is that?
This seems like parent is a struct.
Yeah.
Is a pointer to a struct. Okay? So parent is a pointer to a struct, and that makes P first child a member of that structure. Okay? So we are pushing the member called first child, P first child, of the structure pointed to by parent on the stack as a parameter. Okay, so now we can say, okay, this is a call. Now I'm not really quite sure what we're doing with the result of the call, so let's see what we're doing with the result here. Oh, that's pretty easy. All we're doing is to say, okay, first of all, we are cleaning up the stack. That's just cleaning up the stack so that the 4 bytes used by the parameter is no longer on the stack. And then we take the return value of the subroutine call and put it into result. So that means the instruction that we're dealing with here is just result. Sorry? Oh, sorry. There we go. It's just result equals to the call to node sum.
Plus equals. Plus equals.
It's plus equal to. Yep, you're right. Okay, this is plus equal to because we are adding to it and we're not moving. Good job. And the parameter is the key part here. It is parent points to P first child. Okay. Now we have seen this notation already with the current homework assignment, where the name of the structure forms the prefix of the label, underscore, and then the name of the member of the structure. So I'm just using exactly the same naming convention in this particular question. Okay, what else are we doing here? Okay, looks like some kind of conditional thing going on here, right? Because we have a compare and a conditional branch. So we want to find out, okay, what exactly are we comparing? Once again, we are copying the parent thing, which is a pointer, into EAX, and this time we're referring to another member of parent, which is what in this case, and we're comparing that to 1. If it is not 1, we go to if end, which is down here, and then we have another chance to go to if end, if where, which is a member also of parent, if that is 0, we also want to if end. So combining these two, the corresponding C code is going to be if, okay? So we are checking parent points to what? And we want it to be a 1 to go to the then branch, because if it is not 1, we get out of the conditional statement. So we are saying if it is 1, then we are not going to branch to the end of the conditional statement. But hold on second here. We have a second chance to get to if end. That's when where is a 0. Okay, if you look at this code here, if where is in fact, right here, if where is exactly 0, we also want to branch to the end of the loop, the end of the conditional statement. So that means there are two reasons to get out, which also means the reason to go to the then branch is a conjunction, because we got two reasons to get out. Is that making any sense? Okay. All right. So the second reason that I also need to be true to go to the then branch is the member called where is not null. Now, if you just say parent points to where, it is already implying it is non-zero. But if you want to be extra careful and say, oh, we are comparing to 0 to make sure it is non-zero, there's no harm in saying, okay, let's make sure it is non-zero. So that's perfectly okay, even though syntactically or semantically, it is not necessary. Is that okay? All right, so now we have a conditional statement. Does not appear to have an else, okay? So we have just the conditional statement having the then branch. Inside the then branch is just these three statements here. Okay, so let's figure out how to do these three in C or C++. The first one is to copy the where member of parent, or what the structure pointed to by parent, to EDX, and then we do an indirect EDX to EDX, which means we're dereferencing, and then we put EDX into result. We add it to result. So that means, once again, we have result plus equal to, okay, that's implied by the last instruction, but the other one implies we have a dereference first. So there's a dereference here. What are we dereferencing? Well, we're dereferencing whatever is in EDX, and what is in EDX? It's the member where of parent. So we have parent points to where inside the dereference. Is that okay? More or less? Okay. And I think that's the entire thing. Oh, wait, there's a little bit more code after this, after the inner conditional statement, so I'm gonna use this symbol to imply that I just forgot something, okay? So this is inserting stuff in between the two end curly braces. Okay, move parent into EAX. I'm reading this instruction here. Move parent into EAX, and then what are we doing with EAX? We're not pushing EAX itself on the stack, we're pushing P next sibling, which is a member, onto the stack. And then we called node sum, we clean it up, and then we add the result of that function call into my local variable result here. So that means this code is boiling down to result plus equal to. The result plus equal to can be implied by this instruction here. And what are we adding to result? Well, whatever the result of the call is. The call is to node sum, and we know we're calling node sum because it is spelled out here, called node sum. What are we passing to node sum this time? It is the next sibling member of parent. So parent points to P next sibling. Okay, running out of space here, but it's close enough. Okay. Yeah. But the idea is it's just the member P next sibling.
It will compile. It will compile.
Well, as long as I can read it, it's good. Okay. All right. So this is the algorithm, and now we have to go back and figure out. Okay, is parent going to be a local variable, or is parent going to be a parameter? What do you think? Just by the use of parent, what do you think?
Parameter.
It's a parameter, but how do you know that parent is a parameter but not a local variable?
Because we never set parent to have a value.
Exactly, because if parent was a local variable, it never had any initialization code, which means we'll be using a dangling pointer. Okay, so that means parent has to be a parameter, which goes up here. And what is the type of parent? Well, okay, there are several simple things that we can consider first. Is parent going to be an int? From the way I use parent, is it an integer?
It's 32-bit.
Well, it's 32-bit, but is it an integer?
I think it's a pointer.
It's a pointer. Very good. Okay, so we know it's a pointer, so we say it's a pointer. But what is it a pointer to? What kind of things is it pointing to? So it depends on how we use it inside the subroutine here. Okay? Apparently, it is a pointer to a structure, right? Because we use node where and node what and stuff like that after we put parent into EAX, and then we use EAX as a base register. So that means parent is a pointer to a structure. Can we imply the name of the structure by the way I use the labels? Node. Okay, just struct node. Very good. So we say struct node. Parent is a pointer to a struct node. Now, am I changing anything that parent is pointing to? Do we see any assignment statements where the left-hand side is a member that parent is pointing to? We don't. And what other functions are we calling from here?
It's just itself.
It's itself, okay? So that means if this subroutine is not changing anything that parent is pointing to, the other subroutine that we are calling cannot be doing that either because it's recursive and it's only calling itself. So I'm not going to put any point values to this one, but you can also say const struct pointed to because we know it's not changing the structure that it's pointing to. But it's not going to be required because that's really like some additional stuff that you have to deal with. Okay, so given all that stuff, do we have any idea of what result is supposed to be and how the type of result relates to the return value type of the subroutine itself? They should be the same, right? Okay, now how do I know they're supposed to be the same? It's because of this instruction here. I am just copying result, which is a local variable, into EAX, which means if result is signed, so should be the function. If result is unsigned, so should be the function. Do we have any indications whatsoever whether it should be signed or not? Do we see anything like JG, JL, JB, JA, that sort of thing? No. All we saw was JZ, JNZ, which does not imply the signedness of the whole thing. So that means what you can do is simply to say, okay, it can be int here, but then it also has to be int here. If you say unsigned, make sure they are both unsigned. That's all. Okay, just pick one of those two and say it can be one or the other, but they just have to be consistent. And that's the whole thing. So what is new here that you did not see in your homework assignment is the use of a pointer to a structure, because in the homework assignment, we are only passing structures by value. We're copying the whole thing onto the stack, okay, and we're returning the whole thing. But in this case, we're not passing the entire structure by value. We're passing a pointer to a structure. So that part is definitely new. Well, okay, it's new in a way, but it's also not new in some other way. It's just a combination of the concept of dereferencing, pointers, and structures. Are we doing okay so far with this particular question? Is it good? Okay, all right. Moving on to question number 3. Okay, given the following structure is defined in both C, is defined both in C, and the appropriate labels are defined in assembly labels, which means if we have a scanf underscore FMT, where and result, and also an scanf underscore size of, or just size, implement the following 2 subroutines in assembly. You may assume the usual labels are already defined, so you don't have to waste time to do that. And no need to worry about the include file in this case. Note that the callee is responsible to deallocate the pointer to the return value area, which basically means you have to use an RET and then $4 to get rid of those extra 4 bytes. Okay. The prototype of Mem Copy is this, which by now you probably should know already because you have used it quite a few times in your homework assignment. So these are the two functions that we're dealing with. All right. So how do we get these two done? And the thing with this, I can probably just use an on-screen editor. Could have done that with the other one too. I just forgot that I have this option. There we go. All right. So we'll deal with scanf int first, scanf integer, and we'll figure out how to do that. All right. So what do you think? Let's start, because the question said, we have everything else, all the labels already defined, the usual way. So I feel free to just start with the label definition and the return down here. So I can now say the usual thing, push LEBP, push LEBP, set up the frame pointer, and recover the stack pointer at the end. And also remember to allocate for the local variable, which is s in this case. Okay, so this is all taken care of. Now that we are done with the entry code and the exit code, we can now focus on the actual code inside the subroutine. So the first statement inside the subroutine is we want to initialize the member FMT with a string called, with the actual content of %d. We have done this already in the homework assignment, okay? To deal with literal strings, you just have to define it somewhere, within your code. So within your code here, before the label of the function, you just have to say, FMT string or whatever name, you can name it whichever way you want to, and then .ASCIIs, but you have to make sure this is ASCIIs with a Z at the end because we want it to be null terminated. And then in there, you just say, okay, %d, that's it, that's all you need to do to declare the literal string. So inside the subroutine, you just have to say the member FMT is going to have that value. Okay, s is my local variable, so that means this should do it. $FMT str, which is referring to the address of the .ASCII's initialized string, and we want to copy this into the FMT member of scanf. So scanf underscore FMT refers to the offset or the number of bytes between that member and the beginning of a structure. And the structure itself is called s, which is a local variable. And in order to access any local variable, we have to use EBP because that's the frame pointer. So are there any questions about this? This one single instruction is actually implementing this entire thing. Are we doing okay so far with that? Okay. So, oops, I got my focus on the wrong screen. So the second one seems to be pretty much just as easy, but it's not. Because if you use the usual way or the short way of doing it, which is going to be something like this, because PINT is a parameter, and that means it is also relative to the frame pointer, and where is a member of scanf, the structure. So we want to be able to do something like this, but we can't because there are two memory operands in this case. So that means you have to break it up into two instructions and connect these two using a register. And I'll just pick EAX because EAX is a register that you are free to use. The last one is easy because we just want to put a 0 into result. So for the most part, I can just copy and paste this here and change the FMT string, the format string, to 0, and then change the member FMT to result, just like that. Now we are going to return s as the return value, and this is where you need to do the Mem Copy thing. And I'm guessing the majority of this class do remember how to do Mem Copy because you have to do it many times in your homework assignment. So what is the last parameter that we have to push?
Size of.
The size of, okay, the number of bytes to push, the number of bytes to copy. So in this case, the label scanf underscore size or size of has the number of bytes. And the second parameter is, nope, is the source. So where we are copying from. In this case, we are copying from the local variable s. So I need to push the address of the local variable s on the stack. And there are many ways to do this. This is just one way. You push the frame pointer itself, and then you do the calculation after the fact on the stack. Okay. So that's one way to do it. You can also do the calculation with a register like EAX and then push EAX on the stack. Either way is okay. You know, you can pick one or the other. Are there any questions at this point? This is my second parameter. The first parameter is the destination. And where is the destination? What label do I usually use in my examples for the destination? Return value address or PTR. Okay, so as long as it's something like that, you know, I can accept it as an answer. So now that we have all the parameters pushed, we can call Mem Copy. And we have to remember to undo these 12 bytes because we don't need them anymore. So that's why, you know, in the description of the exam, I specifically said, you know, what I consider as correct code is I have to make sure that we clean up after this kind of thing. Yep.
Since it's returning a structure, we do return $4 for the return?
Yes, so the return has to have $4. In fact, that was emphasized in the question itself. Good job. So we have $4 here, because in the question I specifically spelled that out. The callee, which is the subroutine that you're writing, is responsible to deallocate the pointer to the return value area. So good job, you caught it. So are there any questions about the implementation of scanf int, which is this particular subroutine in C? Yep.
In the line file, is that an add L or something?
You mean this one here?
Yeah.
That's an add L. Because as a local variable, the label s is a negative value. Okay. All right, so if this is done, then we move on to scanf1, and which is not going to be too bad. Okay, so scanf1 has a subroutine. Okay, in this case, should I return 4 or not? Yep, because it's the same setup. Okay, so we return 4. And then we have the usual stuff. I'm sorry that I can just kind of copy and paste here, that you cannot do it in the exam. Okay, so all this stuff already set up. No local variables, so we don't have to adjust the stack because of local variables. And in this case, we just have to push where, push fmt, call scanf, store the result into result. Yep.
How do you already know you're gonna have to return 4?
Because we are returning a structure by value. That's how I know. Every time you return a structure and not a pointer, not an integer, you have to do the return $4, because you will be passed a return value pointer with this type of subroutines. Okay. All right, so getting back to here, and I already know what I need to do to return. Okay, so I'm just gonna copy and paste this stuff here. Okay, that deals with the actual return s at the end of the subroutine. So what is left here is just calling scanf, store the result into result. So it's just a bunch of push instruction. We have to push scanf underscore where plus s relative to EVP. That's my second parameter. And then scanf underscore fmt plus s. That's my first parameter. Call the subroutine scanf. Now, what if you don't know what scanf does? Would that matter?
No.
Nope, would not matter at all, because that's, if the subroutine, if it's saying just push these things, push those things, undo or deallocate those 8 bytes. And then we have to store EAX into result, because that's the return value of scanf. So move our EAX into scanf underscore result plus S EBP. And that's it. That's the entire subroutine. Yep.
How do we know it's 8 bytes?
How do we know?
It's 8 bytes.
How do you know what is 8 bytes?
Because you push 2 variables.
Because
they're
these two are
both-
push L's. Each one is a L, so each one is pushing along. Yep. And also in here, I spelled out the members already. And in the 32-bit architecture, a void pointer is 32-bit wide, and the integer is 32-bit wide as well. So in the test, if you have doubt about the implied width of a type, you can ask me. Or in this case, if you have questions about the implied result type of scanf, you can ask me as well. Yep. Mm-hmm.
So in your code that you wrote,
Okay.
why is the last line moving the variable into EAX and not the other, or not, why isn't it the other way around? Why are we moving EAX into something?
You mean here?
The very last line. I mean, the last one before we.
Or the one before?
Wait. No, never mind. I guess I read it wrong. Never mind.
Okay. Yep.
How would we know when it's not 32-bit long?
If I say long, then it's not 32-bit.
No, I mean, would it be something like within the lines where you're just using just BL, just like the ending of the registers, and
Oh, okay. So
you're
in
just
the-
using those, and then
In the assembly code, if I
Yeah.
use compare byte, then you know it is 8-bit wide.
and so if you'd have 2 of those, like 2 variables like that, that would be just bytes. Then there would be
A word.
you'd have to add a 2.
Oh, you mean
Instead
to
of
recover?
8? Yeah, the recovery.
You mean to recover the space on the stack?
Mhm.
Well, how do you want to recover from the stack? This statement here directly relate to how you push the parameters.
So if there would be push B,
There's no such thing as push B.
okay. what other thing is there?
There's no such thing as push B, and all the subroutines usually require that you pass as integers. So if you have a character that you're passing, but you have to pass it as an integer, you have to do the full sign extension thing to make sure you're pushing 32-bit. Any other questions about number 3? No questions about number 3? So now we can look at question number 4, which is based on question number 3, based on the same definitions. So in this case, we don't want to implement the entire subroutine. We just want to implement the following code fragment with an emphasis on fragment, which means you don't need a full definition of the entire thing, just the code that is here. You can assume all the labels are properly defined at this point. X is an integer local variable in the context of this question. So this X here is a local variable. Okay, so given that is the given, let's figure out the code to do this. Go. All right. This is a conditional statement, but I'm not even concerned about the conditional part until I can get to the result that we are comparing. So what you need to do to look at this one is to say, well, this looks kind of complicated because we have this dot notation, which means result is referring to a member of a structure. What is that structure? Oh, this whole thing is going to give me the structure. But that's a function call. Can a function call give me a structure?
Yeah.
Oh yeah, I mean, you guys have done it already. It's just that in your program, we don't do it this way. We don't immediately use the return value of a function and then just say, oh, I don't care about the entire structure. I just want to know one member of the structure. But we can certainly do it like that. So we just have to implement the function one thing at a time, starting with the innermost part. So we are passing the address of x, which is an integer as a local variable, to scanf int. So let's figure out how to do that. Okay, x is a local variable, which means it is relative to EBP. So that means if we want to push it as a parameter, we can push EBP first, and then we do the adjustment like this. Then we would have pushed the address of x on the stack. Any questions about this part? Is this part okay? So now that we have the address of x on the stack, the only thing we have to do is to call scanf int. So call scanf int. But wait, there's a problem here, because scanf int is not just a subroutine returning a integer or a scalar. What is it returning? Let's go back here. Scanf int returns a structure. So from the caller's perspective, how do you set up to call a subroutine that returns an entire structure? So this won't work, not yet. So what do we need to do? We have to allocate space. Okay. So should I allocate space before I push the parameter %x or after? This is also directly related to the subroutine ABC in your homework assignment, because ultimately what we want to do is to call scanf1, which is expecting a parameter that is a structure. Is that okay? So that means I want to allocate that space first, and then just have scanf int to make that space initialized. That's what we want to do. So that means even though this instruction is useful, I don't want to do it just yet, okay? What I want to do is to reserve all that space on the stack. To reserve space on the stack, given the number of bytes that you need to reserve, you just have to spell it out and say, okay, let's subtract this number from the stack pointer. So in this case, we have scanf as the name of the structure. The size of that is the number of bytes of each structure. We subtract this much from the stack pointer. That will reserve that much space on the stack. And then we push all of this stuff on the stack here. And now we have a hidden parameter, because any subroutine that is supposed to return a structure has a hidden parameter which we call the return value pointer or the return value address. So it is time to push that now. There are two ways to do this. Okay, I'll do it the more obvious way this time. I'm going to copy the stack pointer into EAX first. But I don't want to just push EAX at this point because it is not the right place. How many bytes am I off from where it is supposed to be? Okay, think about the sequence of all the stack related operations. So I'm going to put not quite 8. Okay, you're close. No. Does anyone want to try 7? Or 7.5?
Don't make me cry.
Or pick some irrational numbers. Okay, so let's see what is happening here. The stack pointer is originally here. Okay, this is called ESP, and this is initially the condition. So after the subtract long instruction, I would have reserved enough space for a uppercase scanf. So this is the struct scanf here. This is step 2. The stack pointer is now here, and this is after the subtraction, subtract long $something from ESP. Okay, this is step number 2. And then we decide to push the address of x on the stack. So this is the address of x. And this is step 3. The stack pointer is now here. And now we want to push the address of the structure. We want this to point back to the base of here. And the stack pointer is now here. So the question is, based on the stack pointer at this point, this is step number 4, how do I calculate the address of what where it's supposed to be? Now remember, I have not pushed the return value address yet at this point. In other words, when you look at the code here, we only have one push long here. I'm just doing the calculation using a register. So how should I adjust EAX so that it is pointing to the base of the structure that I have allocated earlier.
Just a +4?
+4, very good, good job. So in the code here, what I need to do is just do an add long $4 to EAX, and then we can just push EAX on the stack. Is that okay? So if I want to comment, this is the actual parameter, and this one is the return value address that we have to push on the stack. Then we can proceed and call the subroutine. So if I switch back here to the C code, we have to call the subroutine called scanf1, scanf1, nope, take it back, scanfint. And after that, we have to kind of deallocate something from the stack. So how many bytes should I deallocate from the stack? I have 2 push longs here, but there's one thing that we have to remember. How many, okay, I know that I have to add something to the stack pointer. So the question is, how much should I add to the stack pointer to undo what is left on the stack? 4 bytes, very good, not 8, because the other 4 bytes were deallocated by the callee. Okay, good job. So at this point, if I go back to the document camera, so at this point, I would have these 2 will be deallocated. I'll be pointing back here, and that is that the right thing? You know, this is what is left on the stack. Is that the right thing in order to call scanf1? Let's check the prototype of scanf1. So scroll back a little bit. Scanf1 is expecting a scanf structure, and if we look at the structure here, this is what is left on the stack at this point. Is that okay? That's exactly what we want, isn't it? Now, what about scanf1? What does it return? If you look at the code of scanf1, it returns a structure as well. So we have to kind of give it a space to return as well. So that means in the assembly code here, we're missing something. We should have allocated twice of this much initially. Is that making any sense?
Is that correct? Or format, you're allowed to do 2 asterisks?
Yeah, you can do that. Because scanf underscore sizeof is really just a number, like 8, 12, or something like that. So 2 times 8 or 2 times 12 is resolvable by the assembler, and that's going to be okay. If you doubt that this can be done, you can just do this twice.
Mm-hmm.
Are you doing that twice because you're essentially returning twice, right?
Correct. Well, yeah, you can do it twice, just like that. But this won't impact the rest of the code. We just have to find the use of that later on. Okay, so at this point, we are done with the inner call, and we are ready for the outer call. But there's one more thing we have to push on the stack first. So we have to push the return value address of the other structure. Okay, so where do we find that? Let's look at the document viewer. Okay, so the picture has changed just a little bit, not really a whole lot. So let me see if I can find a blank piece of paper. Okay, so the picture has changed a little bit because we have 2 structures allocated on the stack. Okay, and then we did a whole bunch of stuff, but by the time we get to calling scanf1 over here in this code here, we are actually already back to this stage with 2 scanf structures. So this is one scanf structure, this is another scanf structure. And the stack pointer is currently pointing to the base of the lower one, which contains the parameter to call scanf1. So everything is quote unquote set up fine, except we need a pointer here to point back to here. Is that okay? Because that's going to be my return value pointer. So now how do we do this part here? So I'm going to slide this one over and focus on the actual code.
When we do the first sub L scanf size of, we can store the value of the
We can do that, or
ESP.
we can do it by computation. We can compute the actual address. So once again, I copy ESP into EAX. In other words, I make a copy of ESP so that EAX points to the same place. So the bottom line is I want EAX to point to this location. This is what I want. So how should I adjust EAX so that it points to the Scanf structure that we allocated first and not the second one? Just add the size of a Scanf structure. Very good. So we just say add long scanf scanf size of. Just add that to EAX. Push it on the stack. Now we are ready to call scanf1. Okay. When it returns, we got to clean up the stack again. Once again, the return value pointer or the return value address is deallocated by the callee, so I don't have to undo this particular push long. But I do have the entire structure still on the stack as a parameter, so I do have to deallocate that one. So that means I have to add long the size of a scanf structure, scanf underscore size of. This is for deallocating the parameter itself. So when this is done after the add long instruction, then this stuff will now be gone, and the stack pointer will once again be pointing to the first structure that I have allocated on the stack. Are we still following? Are we still okay with this? Okay. And in the C code, we are pretty close to getting everything done, because at this point we are done with calling this whole thing, and we are left, this entire thing is left with a structure on the stack. And it's up to me to decide, how do you want to use that thing on the stack? Oh, I don't need the whole thing. I really just need one thing out of that entire structure called the result. So in the assembly code, what we want to do is to say, oh, the stack pointer is now pointing to the entire structure. Perfect. So what we'll do is to say, I can do it directly out of the stack pointer, but just for clarity, I think this may be slightly better. So I'm just going to copy that to EAX. And I'm going to say, we want to do a comparison of that to 1, but we only want the result member of the structure that is pointed to by EAX. So we do a compare long, and then we say scanf1 underscore result, which is referring to the member result. And the pointer pointing to the structure is EAX here, and we want to compare that to 1. So we just compare 1 over here. But one thing you have to remember is all this time, the stack pointer is still not, we haven't restored the stack pointer because it's still having an entire structure on the stack that we don't need it anymore after this compare. Is that okay? So what I'm gonna do is, okay, can I do this right here? In order to reclaim that space on the stack, can I do this?
You'd lose the flags.
The flags, exactly. So I cannot do it here, okay? I should not do it before either. Okay, if I take this code here, okay, let's do a cut and copy. That's wrong also. Now, this code would actually run just fine, but it is wrong because at this point, the stack pointer is pointing above the stuff that you need. In other words, if this is not running in an environment where we have a protected operating system, any interrupt that happens now will trash that stuff. Will trash the things that we are going to use, so this is not okay either. Okay, so that means I cannot do the deallocation just yet, okay? We'll do it later. So we do the compare, and then we say if it is 1, we want to add 1 to x. If it is not 1, we are not going to do anything. So we will say jz to nif, and here's the label nif. And by this time, it is safe to deallocate, for that whole structure that is still on the stack. So we just add long $scanf underscore size of, and just add it to the stack pointer to deallocate the structure. And between the jz instruction and the nif, this is where we can just say add 1 to x. Add $1 to x, which is supposed to be a local variable. So that's how we can add 1 to a local variable. All right. So are there any questions about this code here? Is it? Yep. Go ahead.
So that looks like after it calls scanf1 to add long, adding to ESP.
Oh yeah, that is added to ESP. Sorry, I didn't finish that whole instruction. Yep. There we go. And that one is just undoing a parameter to scanf1. Yep. Yep. Mm-hmm.
I'm probably understanding this wrong, but from what it looks like, it's looking like it's set up to jump over if it if it is equal to 1.
Oh, you're right. Okay, jump over if it is not 1. Good job. You spotted. There you go. Good job. Because we want it to be 1 in the then branch, which means to jump over, we want it to be not 1. Good job. Okay. Any questions about number 4? Is it reminding you of the homework assignment? I'm hoping that it kind of, there's one part of this that is not in the homework assignment, which is immediately using the structure returned by a function like this. But other than that part, I think it's very similar to what we have to do in the homework assignment. Okay. So here's question number 5. String compare can be implemented as follows. Okay, so this is just one way to do string compare. It's recursive. The following is the faulty assembly code implementation. And the question is, your job is not to fix it. Once again, we want to figure out, how this code can appear to be correct and when this code is going to be wrong. So let me just read the entire question here. So your job is not to fix it, but to figure out specific cases where this code appears to work and other cases where the symptom would actually show up. The subroutine is supposed to return 0 if 2 strings are the same, a negative 32-bit number if the first string is less than the second one, and a positive 32-bit number if the first string is greater than the second string. In each of the following cases, specify 2 arrays of characters with the values of each character specified. The first array is assumed to pass to the first parameter, and the second array is assumed pass to the second parameter. So this is how I can specify ABC with a null terminator, and then a ASCII code of 1 and ASCII code of 2. Followed by DEF, and then the ASCII 3, ASCII 4, ASCII 5. Okay. And 0T is the prefix of a binary number, by the way. So this is how you specify the test case. So here are the test cases that you have to come up with. I want you to come up with a test case where it returns a 0 when a 0 is supposed to be the return value. So the first thing we have to do is to look at the actual assembly code and figure out what is wrong with it. And then we will have to figure out, okay, how do we make it to seem like it is working correctly? Okay, so this is the actual code. We might want to study this first. Okay, it's not really that much different compared to the usual string compare, except this one is recursive. So we start with a conditional statement that says, if string A and string B, if the first character of the strings are the same, then we want to go through this code here. If the first character of these strings are different already, guess what? We have a conclusion, don't we? Because if they're different, then we already know the strings are different. We have no further need to compare anymore. So as a result, we just have to say, okay, just give me the result of the character pointed by string A minus the character pointed by string B. But this statement here that looks really simple in C is actually not that simple in assembly language. Because I think we have been exposed to this already, that string A and string B are both pointers to characters. But result is an integer. So you have to do sign extension in assembly to make this work. Do you remember that part? Okay. And then the last part here is really easy. We're just returning result here. Inside the recursive call, when string A and string B have exactly the same character, then we say, do we really have to go on? Maybe we have just reached the end of both strings. But if string A points to a non-null character, it means we have not reached the end of these two strings, which means we have to further compare, but using the next the pointer to the next character for both string A and string B. Otherwise, if string A is pointing to a null character, which means I have reached the end of both strings at exactly the same moment, then I can say, hey, they're both the same, just return 0. Not a problem. Is that okay? So that's how the C code is structured. So now we take a look at the assembly code and see if we can spot any problems. The usual stuff, this program is not going to crash because it just misbehaves. So we have all the usual stuff that is already done correctly here. We copy string A, string B into two registers, ECX and EDX. Both of these registers are free to be used, so that's not an issue. We copy one indirect into EAX. We compare EAX to EDX. And then based on the result of that comparison, we go to else. So it means these three instructions are corresponding to this comparison here. I see a problem, do you? Do you see a problem here? And what is the problem? In the original C code, what am I actually comparing? I'm not comparing pointers. Okay, let's go back to the C code and see if we can figure out what we're comparing. In the C code, I'm not comparing the pointers, I'm comparing
the debrief.
What they're pointing to, okay? But based on the types of string A and string B, what do they point to? Each one points to a character. So I'm comparing two characters with this comparison. In the assembly code implementation, what am I comparing? I'm comparing 32-bit chunks, longs, okay? Okay, so the width of the comparison is the problem. It is supposed to be a compare byte, but I have a compare long here. Now your job is not to fix it. Remember, this is not to fix it, but you have to figure out, okay, how is that going to impact my code, and how can I make a test case to still work correctly despite this fault here? So I want two strings to be considered the same when they are actually the same. So you have to kind of come up with a case where that would happen. When is this going to make a difference, and when is it not going to make a difference? The compare long. Yep.
Like it'll make a difference if like the last 8 bytes match. I mean, if the least significant 8 bytes match, but the first significant 8. But the first significant rest of the thing doesn't.
The other 24 bits, okay? The other 24 bits can determine whether the symptom will show up or not, okay? So let's take a look in terms of the memory layout and figure out the case where two strings are supposed to be the same. Even with this fault, it will still be considered the same, and guaranteed so. Okay? So what we want to do is to say we're comparing two strings. Okay, so we'll just go ahead and specify some bytes here. And I just need a simple test case. I don't need anything that is really complicated. So you can come up with the simplest case where this particular problem is masked. Okay, all right. Let's think about two empty strings. Okay, an empty string is pretty easy to represent. We have a null character here. We have a null character here. So these two are null strings to begin with. They're considered the same, and we should have a 0 coming back from string compare. But compare long is not just comparing these two, it's comparing these 4 bytes as if it is one single integer. Okay. So if I don't want the symptom to show up, okay, what do I need to specify as the strings that we are actually comparing? There are many ways to do this. Okay, I just need one way to specify these 2 strings that we are comparing, where the result is seemingly correct, even though the code is wrong.
So just make sure those 3 bytes on both are the same?
Yep, exactly. They just have to be the same. And the easiest way to think about this is, let's just make sure that these are all null characters. Then the symptom is not going to show up. Because the algorithm, okay, when you go back to the assembly code here, so these 2 will now be considered the same, which means the JNZ is not going to happen, and it is going to be a 0. It's a 32-bit 0. Okay, when you look at this code here, because these 4 bytes are all zeros, so together it is representing a 32-bit 0. So the 32-bit 0 is going to match as well here, because this width is also wrong. So we are going to go to the else. Else is going to put a 0 into EAX, and it will jump to endIf, which is all the way up here, and that's how we get out of the entire subroutine. So this is how you kind of make up a test case where the test case is going to mask the problem. The algorithm is actually incorrect, but it won't show up. Are we okay with that? Okay, all right. So now the second question is, return a negative integer when a negative integer should be returned. Okay, so we want to specify a case where once again the problem is masked. Okay, a negative number is actually returned when it is supposed to be returning a negative number. Okay. So for that, let's go ahead and check the rest of this program and see if the rest is correct or not. So we compare the 0, which is the okay, this is the one of the characters pointed to by the pointers, and the else case is just doing the subtraction as a 32-bit operation. Okay. So how can we come up with a case where a negative number is actually returned correctly when it is supposed to be returning a negative number? So let's go back and look at the test case here. Okay, so we have string A, string B. So in the second test case, this time I have to designate one particular one as string A and the other one as string B, because we are dealing with subtraction and that is not commutative. And the key is we are still looking at 4 characters, because we are using 32-bit operations, which means when we compare, we're comparing 32 bits. When we subtract, we're subtracting 32 bits. So now the question is, how can I do this so that the correct result seems to be returning? Well, that's not too hard. We just have to make sure that these are all zeros, so they don't interfere with the actual subtraction. And we just have to make sure that the string A is less than string B. So if we put an ASCII code of A here and the ASCII code of B here, that's going to work. Because what this will end up doing is to subtract the ASCII code of A from, it will do the other way around. It will subtract the ASCII code of B, which is greater than the ASCII code of A, so the end result is going to be -1. Now you look at this kind of funny because it doesn't seem to be right. That's because of little endian. Remember what little endian is? Yep, the least significant byte is the one that has the lowest address. So when we specify a string, we specify the first byte here, the second byte here, the third byte here, and the fourth byte here. But when you look at this as an integer, as a 32-bit integer, this is the most significant byte and this is the least significant byte. So that's why it looks kind of strange, but it is going to work. So are we doing okay so far with the second part of this question? We want the result is supposed to be a negative number, and it does give me a negative number. So let's take a look at the last part. Okay, we're just on time as well. Number 3 is I wanted to return a negative integer when a 0 is supposed to be returned, indicate the actual return value that is incorrect. So in this case, the question is saying a 0 should be returned, which means two strings are supposed to be the same, but instead of returning a 0, it is returning a negative integer. So let me flip to an empty part of my paper here. But now that we understand the nature of the problem that we're dealing with, it's not too bad. Okay, so once again, we have string A and string B, okay? If the two strings are supposed to return a 0, which that means they're supposed to be the same, the simplest two strings that are supposed to be the same are two empty strings, okay? Well, that's easy. Here's an empty string, here's an empty string. So if the algorithm is actually implemented correctly, this would have returned a 0. But I want this faulty subroutine to return a negative number instead of a 0. So what we need to do is to make sure the other bytes are messed up. Okay? So this way, it's going to interfere and say, oh, okay, the first string is actually less than the second string. And the easiest way to do this is simply to change one of the 4 bytes, having the other ones being the same, and just have this one being an A, the ASCII code of A, and this one being the ASCII code of B. That will do it. Because what ends up being the numbers being compared and returned is the first number. Okay, remember in the question, it will say what is the actual value being returned. It's not going to be -1. It's going to be negative 256 in this case, okay? Because what we're subtracting is we're looking at this number is 0, 0, 0, 0, okay? This is the first 0, 0. This is the second 0, 0. And then the ASCII code of A, which is 61 in hexadecimal, and then the 0, 0 here. And then the second number is kind of the same thing, 0, 0, 0, 0, but it has a 6, 2, and a 0, 0 here. So you do the subtraction, 0, 0 is going to be 0, 0. This one is going to be FF. The rest are also going to be FF. And when you look at this number, it is representing negative 256. Okay? So this is how we can answer question number 3, case 3. And then case 4 is returning a positive integer when a negative integer should be returned and indicate the actual incorrect return value. Okay. So now that we understand the nature of the problem, it's actually going to be not too difficult. Okay, so we are looking at two strings again. And everything has to do with the first 4 bytes. In this case, it is supposed to return a positive integer, which means we can have a B, the ASCII code of B here, and the ASCII code of A here, and that alone should end up with a positive number as the return value. We want a null terminator here, so both strings are properly terminated. We still have 2 more bytes to play with, and those 2 is going to make the difference. Because now we can just say one is a null character, so this one has all null characters, whereas this one has a \1, which is just 1 being the ASCII code. It's not the ASCII code of 1, it is 1 as the ASCII code. Okay? Okay, so this case will give me, the algorithm being implemented incorrectly will give me a negative number, but the correct behavior is to give me a positive number of 1. So, yeah, question?
I think you have them reversed. Just
Oh.
the question says it should be negative, and
Oh, okay, you're right. Okay, I got it flipped. Oh, you can do this.
Duck hand cameras and.
Oh,
Well, you can do it, but we just
Yeah,
want to be
that
able to
works.
see.
there we go. So that will do it. I just flipped it. Good job. This really shows the importance of reading questions carefully. You can probably guess that when I was a student, I was probably a B student, not an A student. Okay, but this would get the job done, because the original or the correct behavior is to give me a negative value, but instead it'll give me a positive value when I subtract string A from string B. The actual value returned in this case is going to be string A, which is 0001, 00, and then the ASCII code of A, which is 61 in hexadecimal, and then string B is 000000, and then the ASCII code of B, which is 62. So when you do this subtraction, do you guys want to do subtraction in hexadecimal? Sure. Okay, 1 minus 2 is an F with a borrow. 6 minus 6 is a 0. 0 minus 1 is F with a borrow. This is F with a borrow. This is F with a borrow. And this is going to be a 0 because this borrow is going to cancel out this 1. And then the rest would all be zeros. So it's going to be F, 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 F. And some people will look at this and go, well, F, 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 F is -1. But only when you look at it as a 16-bit number. This is a 32-bit number, which means FFFF is actually representing the value of 65,300, and it's 2 to the power of 16 minus 1. And I think it is that this number?
Probably.
Okay. You can always express the answer just like that. We're good. Is that okay? I mean, do you guys understand? But does everybody understand the nature of the bug? It has to do with byte operations versus long operations. But as a result of that, we can now, have these problems. Okay, there are certain test cases that can mask the problem. It won't show up as a problem. It depends on what is after the no character, the actual no terminator. So that means this is the kind of problem that can happen mostly in C and C++ programming, but more importantly in assembly language programming. There's nothing to help you to make sure you're dealing with the right type, and that's why it happens even more often. All right, so we got all the questions covered. I will be at the lab for those of you who want to kind of look at the solution of the homework assignment. But because one of these questions does resemble the homework assignment a lot, I think that explains quite a bit already. But I will be in the lab to help explain any one of these questions and also the homework assignment.
Can I have your papers?
Yes, you may. This is the first time somebody asked me for
I didn't
the
occur to me
scratch
until
paper.
today.
Thought about it, but then I forget about it.
I need these. Perfect.
But you have to make sense out of it.
Of course, I understand, but it's still like, what did he do in class again? Yeah. Thank you.
Because otherwise, it would seem like it's an artifact that you dig up in Indiana Jones. It's like, oh, we dug up something here, and it has some scribbling. We have no idea what it means.
Would you happen to have like a blank copy of exam 2 somewhere, so like when I watch the video I can just like do my mark off on that, or like would it be possible to like just post a blank?
Yes, I can post that. All right, give me a second to stop the recorder. Where's the recorder? Right here.